is going to be a very quick intro to the first two sections. And the reason for that is that I've already got videos in week 10 slot called 9.1 and 9.2. And you can go there and you can get a lot more detail. But I thought it might be a good idea just to give you a kind of overview of the beginnings of chapter 9. Because what we're dealing with here are essentially called differential equations and how to solve them. If you are an engineer or intend to become an engineer, differential equations are your bread and butter. They're essentially how you will model real life, how you will set up an equation that describes some physical phenomena that you're trying to model. That just means create a function for. And many of the processes that you learn about are described in terms of differential equations. So if you know anything at all, you might already have touched on them. This is going to be a bread and butter thing. This is kind of what you do every day when you do your thing. So you want to be good at these things. I'll give you an idea. We have a single class on Calc 1 and a single class on Calc 2. Differential equations are that important that Olympic College has 2 classes on nothing but solving differential equations. They are called Diff Ec 1 and Diff Ec 2. So I know that if you are an engineer especially, you may already have that in your schedule of things you'll be doing in the future. So it's not my job in chapter 9 to solve or show you everything that is in differential equations. It's a little bit of a taster to tell you what it's about so that when you do eventually do these things, that you'll have some foundation. So here's my intro, 9.1, modeling with differential equations. A differential equation, everybody calls them DE or Diff Ec for short, is simply just an equation with at least one derivative in it. And differential equations are given their name by the highest order of its derivative. So if you have a differential equation like this one, the highest derivative it's got is a first derivative. So these are called first order differential equations. And this second one has a second derivative, you know, the clunky way of doing second derivatives. Also has a first derivative and some other stuff. So it's basically a mixture of x and y and the first derivative, or x's and y's in first, in this case, second derivative. And you would have a third order differential equation. There are many, many types of differential equations. We're only going to deal with 2 particular kinds of first order differential equations. We're going to do variable separable, which is what I hope to get today, which is 9.3. And we're going to show you how you solve differential equations that look like this type, variable separable. And then after that, the other one we're going to deal with is linear first order differential equations. Now, that's not the only kind of differential equations, so we won't do them. For instance, in second order, there are simple second order, there are homogeneous second order differential equations, there are non-homogeneous second order differential equations. Differential equations very often get a name associated with them, because if you can identify what kind of differential equation you've got, you can then figure out what method you're going to use to solve it. For instance, if I was going to do a non-homogeneous second order differential equation, I would use a technique that uses what's called a characteristic equation. In some, you'd use Laplace transforms to solve them. In others, you simply just do some integration if there were simple ones. So this is the language of differential equations. What do we mean when we say a differential equation? We mean these kind of things. How do we name them? The highest order that you can find. Now, when you solve a differential equation, what exactly are you finding? Well, if you take any of these 2 as examples, what you're trying to do is you're trying to find a function y equals some function of x, y equals f of x, that works. In other words, y equals x cubed. If you plug it in here, stick its derivative, it's equal to that. Or y equals sine x. If you take its second derivative and then add its first derivative, then you add y, the whole thing equals x squared. You are trying to solve an equation But the equation isn't going to be x equals 5. It's going to be y is a function of x, right? Y equals x cubed, y equals sine x, whatever it might be. If your solution has a plus c attached to it, you know, like you get in arbitrary integration, which is not a surprise because quite a few of these techniques, these differential equations, are solved by integrating things. If you get an equation that looks like this, it's called a general solution. And if you get it where it's nothing but numbers, in other words, you know everything, we call it a particular solution. Now, we try our best to write down solutions in this form. Y equals x cubed, y equals x minus sine x, that kind of thing. Sometimes you can't. Sometimes the solution is implicit, right? It's x squared plus y cubed all over x, right? And you can't do anything about it, and that is fine. Here's a very simple differential equation. The general solution to this differential equation is y equals x squared plus c. And that is the general solution as plus c. And this one here has a number, so it's a particular solution. And it's not hard. Can you imagine if you differentiated this, you get 2x. So you can see it's a solution. Solutions to differential equations are typically not unique. In this simple case here, as you agree, for every different value of c, you get a slightly different equation. So very often the solution to a differential equation is a whole family of equations. And they don't always need to look the same. It is possible for quite complicated DEs to have quite different solutions. They both work, but they look nothing like each other. One's got e to the x in it and the other's got sine x in it, you know, that kind of thing. And you might say, wow, that's kind of cool. So that's modeling with differential equations. Now we're going to look at even quicker, and then I'll nip over to Canvas. The second section that we're basically just going to do a quick summary of, and that is direction fields. We only really worry about direction fields when we're talking about first order differential equations that look like this, dy by dx, yeah, like that. So dy by dx is a mixed up version of x's and y's. And direction fields are a way to visualize what this equation looks like. So essentially what you do is you choose a point in space like 1, 2, and x is 1 and y is 2, and you put that together and you find the derivative is 1 times 2 is 2, and here you draw a little line whose slope is 2. And then at this point here you do it and it happens to be a slope of 1, and here it's a slope of 0, and I'm making no attempt to be accurate here, but you end up doing a whole load of things that look like that. And that's what's called a direction field. What direction fields do is they allow us to draw what this looks like. Now, there's a lot more to it than just that. What I'm going to show you is what I have in Canvas for you to look at in your own time. And hold on here. There we go. Hopefully you're looking at week 10 recorded Zoom meetings. I don't know if you've actually been here, but here is a video I've made on 9.1, and here's a video on 9.2. And that's what you're going to get all the details for your homework and, you know, to catch up on what we've done because of my illness. Now, if I go home, come on, I hit home, say it again, go. For instance, suppose you would like to draw one of those direction fields, because trying to do it by hand and accurate is a pain in the posterior. So you click on this guy and you go up here and you basically just type in what the function is. So the one that I just did a few seconds ago was what? X squared y. There it would be. Oh, not that way. There we go. And if you take that out, which is not important, can you see our direction field, which is actually a pretty boring one. Let's put something in more interesting. Suppose it was sine x. There, that's kind of interesting. I'll put in a cosine y, that might make it even more interesting. So, what's that? There we go. There. Now, can you see the direction field? That's what we call it. Sometimes it's called a slope field, as other names. Kind of interesting. If you zoom in on it, doesn't it remind, well, to me, doesn't it remind you of like current in a river? Things flowing. And what you're looking at here is a visual representation of the dy by dx equals this guy. Now, what we're looking at, if I just click on that one there, right, whatever point that is, -3,2 roughly. That guy there, the slope of that line is what you get if you did the sine of the first guy, cosine of the second guy. Now, what you can then do when you have a direction field is, if someone tells you a single point, like in this case, 0, 1, the way I visualize it, can you imagine this is a river current and you have a little paper boat and you drop it at that point? That paper boat will follow the current. It will follow the direction field. So it goes horizontal and then it hits here and then it goes like this. And can you see this one kind of, how it kind of ripples up and down like some kind of cosine thing? That particular paper boat would zigzag down the river, right? In other situations, if I put in a different direction field, let's pick some pretty straightforwards, like what's XY look like? Yeah. Now, if you do this one, can you see at this point here, basically the curve just kind of goes up the way, and on this side it goes up the way. It would look like a quadratic, wouldn't it? For instance, if I chose a point here, can you see that the curve that you would get would be that? Those curves, right, those pathways that you're drawing are actually solutions to the differential equation, right? They're one particular solution. Right? If you choose any point, like this point here, can you imagine what the derivative would do? It would come down, it would hit here, curve back up. And that is really for future reference. So that's what you have to catch up on your own. So what we're going to do now is start the new stuff. Let's figure out how to solve a differential equation. In particular, a first order variable separable one. If you can rewrite your differential equation as dy by dx equals a fraction, and on the top there's nothing but x's, and on the bottom there's nothing but y's, you can solve that differential equation by quite interesting technique. So let's show you how that works in my usual step one. Let's suppose I have a differential equation that is variable separable. And it's that guy. Now, step one involves some sneaky algebra. You have to take this right-hand side and you have to do it in such a way that it's a fraction. And on the top, there's nothing but x's, and on the bottom, there's nothing but y's. So step one typically will involve you having to do some algebra to make this happen. Okay, x squared y cubed. Would you agree that x squared is okay? It can stay where it is, don't need to change it, just call it x squared. How am I going to get that y cubed to be on the bottom but still to be algebraically equivalent to the original. What will the y become when you put it on the bottom?
Y to the -3.
Agreed. So do you see that that's a little artificial, but you have to do it for this to work? So your step one is get it to be a fraction with x's on the top and y's on the bottom. Step two is going to involve this trick. This notation is really helpful for this technique. I could have called that, y dashed or something, right? But I didn't. I choose to leave it as divided by dx. Can you see a little like u sub crossover thing going on here? And what you get is that this guy is equal to that guy. If I take out the integral sign for a minute, isn't that like a cross multiplication? Now, you now have a beginnings of the solution. What we now do is we integrate, which is very common in differential equations. And this guy is going to be the power rule, add c. This guy is going to be add 1 to the power and divide by the new power. We're about 70% finished. Would you agree that we now have the solution, but maybe not in a very pretty format, right? What we have to do in step 3, and that can sometimes be the biggest step, is we have to make this, if at all possible, into the format y equals a function of x. So first thing I'm going to do is not very clever. I'm just going to call that negative power, that guy. So far, so good. Now you can do this in all sorts of different ways. I am going to just multiply everybody by -2. Now, if you multiply this guy by -2, you get 1 over y squared. If you multiply this guy by -2, you get that. If you multiply this guy by -2, you get -2c. And here's a little stinker for you. I'll just rewrite this line again at the top. We don't leave that guy as -2c. We call him that. Now, it's a funny kind of algebra, but here goes. Would you agree that this plus c is an arbitrary constant? It just means a number we don't know. It's a placeholder for a number like 5, right? We don't know what it is, but we know it's a constant. Would you agree that -2c is just an arbitrary constant? I still don't know who you are. Multiplying you by -2 is not going to make it any more obvious who you are. If you don't know what it is, just call it plus c. Are you okay with that, right? So 5 times c isn't called 5c. 5 times c is just called c. 1 over c isn't called 1 over c. It's just called c, right? So anything that you do to c doesn't really change it. You just call it plus c. It just means it's a guy I don't know, and I still don't know who you are. Now, the algebra of getting this to be y equals really depends on what you've got. Anybody, any ideas how I get y squared? What should I do? One over y squared is this. What's y squared going to be?
1 over that.
Yeah. Now in this case, the plus c can stay put. Now, almost finished now. What will I do to both sides to write down what y is?
Square root.
Square root. Now, typically when you do a square root, you do a plus or minus, but you will find that very often in these questions, they have a little guy like this at the beginning of the question. And what that's basically doing is saying, look, when you get to here, only use the plus filler. Now, that is step 3. We have solved our first differential equation, or first order variable separable differential equation. Do you notice it's got a plus c in it? That makes this a general solution to that differential equation. But it's not uncommon that they tell you something like this. Y of 1 equals 2. What that means is that when x is 1, y is 2. That's how you read that. Now, if you tell me this piece of extra information, it is why you end up with step 4. Basically, in step 4, you find C. And you do that so that you can get a particular solution to the differential equation. So if you go and tell me that when x is 1, y is 2, I go here. And I say, okay, x is 1. What does that get me? Well, 1 cube still 1, so I get negative 2/3 add c, and you tell me y is 2. And when I solve this equation, I will find c. And when I find c, I can then return to here and replace it with the number, and we will now have our particular solution. Okay, so again, it's pure algebra. Tell me what to do to both sides. It's going to eventually help me to get C.
Square it.
Okay, as long as you do it to both sides, it's okay. Roll. It's kind of undoing what we did here. Okay, so far so good. There are a couple of different techniques for where to go next. I'm not saying one is better than the other. Any suggestions for what the next line might look like?
Flip. So it's 1/4 equals negative 2/3 plus c.
Yeah, that works for me. Cross multiply is another technique if you want to do that. Okay, where are we off to now?
Add 2/3.
Okay, I'll turn these into 12s. So that's 3 and 8, so it's 11/12. So we have our solution. Our particular solution is y equals the square root of 1 over negative 2/3 x cubed instead of plus c plus 11/12. And that guy there is called the particular solution to our differential equation. And that's basically the template for every variable separable you're ever going to meet. You're going to rearrange it as a fraction with x's on the top, y's on the bottom. You're then going to do this crossover integration thing. Very often this doesn't require a lot of work. Here it was virtually no work at all. Once you've got that done, your goal is to get y equals. And that depends on what you get here, how easy that's going to be. But eventually we got this fella. And that may be the end of the question. But if you're told, it's very often called an initial or boundary condition like this, what that means is that you can now take your general solution and find C. And then you go and you solve for C. And then you replace that with the C that you found. And you're done. a lot of algebra, right? Not that much calculus if you think about it. And the only calculus we did was this line, right? It's hardly any at all. Any questions?
There was a
How
question.
come
Chat.
in
Mhm.
step two,
Go for it.
how come in step two, the Y doesn't get a plus C?
Oh, good question. Technically, it does. It gets a plus D. And then what I do is I take that plus D and I pick it up and I bring it over here as a minus D. And isn't C take away D just a number I don't know?
Yeah.
And so when you don't know what it is, you just keep calling it plus C all the time.
Okay.
And you typically give it to the X side.
Okay. Yeah, that makes sense.
Okay, let me find one of the homework questions if I can. Okay, we're good. So this one is going to be similar to question 1. And it's a first order variable separable. So far, so good, right? Now, our first step is to get fractions. Agreed? Are we comfortable about the 3x squared on the top and the y to the -2 in the bottom? Kind of like the one we just did. So that would be set 1, right? If you do the little crossover deal, you get this guy is equal to that guy. That would be coming up in step 2 now. Okay, this fella, power rule, plus a C. This guy, add 1 to power, divide by new power, and rearrange it. It looks like this guy. Now, the brave amongst you could probably do this in 2 goes. I'm not going to. I'm going to multiply everybody by -1. Did you notice that it's not x cubed minus c, but x cubed plus c? Right. You don't know who c is, plus you don't know me, minus you don't know me, same information, so just call it plus c. Right, virtually home and dry here. What will I do to get y equals in this case? I get 1 over y is this cubic. What's y going to be equal to?
Y is going to be equal to -x to the -3rd power.
No,
Oh,
it's going to be 1 over the whole ugly mess. Do you see it? Reciprocal. Reciprocal. If it was just x cubed on its own, then you could say what you just said. But that plus c kind of stops that from happening. Are we good with that? And this is us finished because there is no extra information. You know, there wasn't any y of 0 equals 10 or something. So that's our general solution. Okay, let's try another one. Let's do this fella. Y dashed 3x e to the y equals 0. Well, for starters, I don't use y dashed. That notation is not helpful in solving this equation. Okay, where are we going next is I need dy by dx equals whatever. So what I'm going to do now is that. And since I've got dy by dx isolated, I should be able to write this as a fraction. Okay, what goes on the top, the numerator of this fraction? What goes on the top here?
Negative 3x.
Correct. How are we going to rewrite that e to the y so it now looks the way it needs to look by being on the bottom?
E to the negative y.
Is there a little bit of a theme happening here that you can begin to see? Right. Now, if you can get the derivative equal to a fraction with x's on the top and y's on the bottom, you can then do the crossover step, which basically means that you can separate them and integrate at the same time. Now, if you integrate this guy, you get e to the negative y with a negative on it. And this guy, if you do a power rule, you get that. Now, remember the goal here is to get y equals if at all possible. Now, since there's only a single y over here, I know it's doable. If you get a question where it's y cubed plus 4y or e to the y plus sine y, something like that, you're never going to be able to get it as a y equals, so don't worry. But if there's only one term here, whether it's y cubed, whatever, you know it's doable. What do you think I should do to both sides to make it a little bit prettier?
Is it the natural log would undo it?
It certainly will, but before I do that line, which is going to be the one after this line, what do you think I should take care of first before I do the natural log thing?
Oh, the negatives.
Right. Now, some of you, are we okay with that plus c still being plus c? We're getting kind of comfortable with that little trick that we use. Right. Negative. I know it says negative c, but we call negative c plus c. Now, if you take the natural log of both sides, have you noticed that that's a package now? You can't separate it. You get that guy. And to get y, you get that guy. And we're finished because this particular one, that's our general solution. That's all we have to work with. Okay, how about this fella? First derivative. Now, I know I need a fraction, and I know from experience that that 4x is good. You might think that I'm going to write y squared plus 1 to the power of negative 1, which would be algebraically correct, but I am not going to call it that. I'm going to call it that guy. Why am I rewriting this fella not as y squared plus 1 to the power of negative 1, but why am I writing it as a fraction? What would be the motivation behind that, do you think?
Is it going to be easier to integrate because it's inverse tangent or whatever that ends up being?
That's exactly the reason. No other reason except that. So when we do the crossover, would you agree that 1 over y squared plus 1 is relatively obvious what its integral is? If I'd left it as y squared plus 1 to the power of negative 1, can you see how that might distract me away from the integral? I might not even realize that it's an inverse tan. Well, with respect to y, this is an inverse tan. And this guy is just a basic power rule, we add c. Okay, we're almost finished with this one. What would I do to both sides to get y?
Would you take the tangent of both sides?
You would indeed. And again, this question doesn't have any y of 0 equals 10 going on. If it did, I'd find c, so that's us finished. That's our general solution. if you like puzzles. Differential equations are fun because of all the little algebra tricks that you need to do. So here is a massively ugly one. So it is dp by dt instead of dy by dx, and it's equal to t squared p take away 3p plus t squared take away 3. Now, superficially, you would say these are not separable, right? They're not, you can't break them into t's and p's, right? You can't separate them, but they are.
Is it factorable?
It is. Anybody want if I showed it factoring? Don't try and factor it in one go. I want you to factor just these two guys and leave these two guys alone. So only from these two terms, what factor can you get? T squared p take away 3p.
Is
What
it going
can
to
you-
be like T1/2 P?
No, nothing as weird as that. More obvious. TP take away 3p.
Do you just take out the p?
Yeah. If I put a little bracket around this guy, do you recognize that this guy and this guy are essentially common factors of this guy? So you got a p plus one of these. Have you seen that this expression actually factored? That was kind of weird, wasn't it? Now, if things can be multiplied together, can they also be separated then? So let's see what that would look like. What do I want on the top? T's or P's? What do I want on the top?
T.
P.
So I can leave the t squared minus 3 on the top then, can't I? Now, doesn't that mean I want this guy on the bottom? Now, I could call him p plus 1 to the negative 1, but I'm not. I'm going to call him that guy. Can you see it's the same kind of reason we did the x squared plus 1 or the y squared plus 1 guy? It's so that when we do the integration, it's going to be nicer. So let's do that crossover. We have this guy. And that guy. So we started off with this horrible mess. After a few lines, we managed to factor it. Because we factored it, it was allowing us then to separate them. Now you do the crossover, we're at this stage. Now this fella here is a natural log. And this guy is a power rule. And I want this to be P equals. Okay, tell me what to do to both sides to get closer to P equals.
You raise it to the e power.
Okay, so what you would get is P plus 1 e to that guy. What would I do to both sides now to get P?
Minus 1.
And as far as I'm concerned, I'm happy with the answer. But the algebra of what's going on here can be rewritten differently. This thing here can be written as e to the c times e to the 1/3 t cubed take away 3t, take away 1. You know, plus becomes this guy. What do you think e to the power of c could be called?
Is that still just C?
Yeah. And that would be another equivalent in every way to this one. Don't think of this c as a fixed unknown value. Think of it as a placeholder for a number you don't know. And if you can put it here, you can put a different version of it here. But mathematically, they are equivalent. You'll probably quit on that line, I would suspect. But, you know, maybe you want to play about with it a little bit more, you can get that. Any questions?
That is trippy.
It's kind of cool as well, right? Bit sneaky, for sure. Any questions? Are we good? Right, last one. Eversion of 6. Not quite sure how much of this I'll get done, but at least it's a good start. This is a differential equation that should be variable separable, but certainly doesn't look very separable right now. In fact, it doesn't even look like derivative equals a fraction. What do you think I should do to both sides to get it at least on the road to fixing?
Would it be dz over dt equals -2 or -2 like parentheses e to the t times e to the z?
Right. For those who don't like too many steps, it was that guy first. And isn't an e to the t plus a z the same as an e to the t times an ez? Do you see how we're beginning to separate? If you can write them down as things multiplied, you can convert them into two fractions. Would you agree that the top gets the e to the t guy? And this fella, well, he's just going to become e to the negative z on the bottom there. Right, we separated them. T's on the top, z's on the bottom. We can do the crossover now. The integration is typically not that difficult. Looking at that guy, right? Integrate that guy, you get negative e to negative z. Integrate that guy, you really don't get much, plus a c. Right, the next few lines are, eventually we're going to get z equals, but we take it one step at a time. How about multiply both sides by -1? That gets me this guy. We should be comfortable about the plus c trick. Okay, now it's the algebra. What shall I do to both sides to get closer to z being on its own?
Natural log.
If you take the natural log of this side, you get negative z, and the natural log of this whole thing is a package now. You can't separate them. And would you agree then that all I need to do is an extra multiplied by -1. And there's our general solution. Hey, we are solving first order differential equations, variable separable. An awful lot of algebra, right?
Is there no way to simplify the right side? Because if c is any number, could you factor out like a 2 in order to have ln of 2 times, or ln, wouldn't it be ln of 2 plus ln of e to the t plus c?
You could.
Just make it uglier, but
Yeah, probably. Yeah, you could do that. You could just call it 2 lots of e to the t plus c again, right? Because half a c is still counts as a c. And you could suck out the log 2 as a constant term. And it would still leave you with an e to the t and a c and a minus floating around. So it wouldn't really be of any great benefit. But yeah, you could do that. Okay, that is us for today. I like what we did today. We did some fun algebra. Hopefully you were comfortable with it. And I shall see you tomorrow where we'll get to finish these guys off. So last name and bye-bye. I'll hang about for questions. Excuse me. Any questions? Was that cool stuff today, Maggie?
Yes, definitely.
Did you like the algebra or you weren't so keen on the algebra?
No, I liked it. There were some parts with that confused me, but then when they were explained, it made sense.
Right. Are you okay with the plus C kind of impervious to things happening to it?
Yes, that has been, it was difficult for me to learn at first, but yes, I do understand it now.
Okay. Anybody got a question?
Yeah, I got one about the first question on the test.
Oh yes, that's right, Eric.
Yeah, how would you solve that one?
Now, if I can remember correctly, it was something like 1/5. Oh, let's split it onto the.
I think it was 5 over x minus 2 times x squared plus 1, I think.
Yeah, I agree. So it was the guy that looked like that. What you got to recognize is that this is essentially a partial fractions question. So you're going to have to split it. It's a long question. In other words, it's going to take us a fair amount of time. But that's how it splits. Then we're going to have to do the general algebraic method. So this guy gets multiplied by x squared plus 1 top and bottom. And this guy here, this fraction here, gets multiplied by x minus 2 top and bottom. So what we end up with is a lots of x squared plus 1 plus bx plus c times x minus 2 is equal to 5 because the bottoms are the same. And I'll start by doing choose x equals 2. And the reason I chose that is it makes this 0. So what do I get? I get 5 equals a, 2 squared plus 1 plus a whole load of nothing. So 5 is 5a, so a is 1. So I can then,
I think from here I know how to do it.
okay. So
Yeah,
basically,
so
yeah.
I was just getting it set up. And this is called the general algebraic method?
This is the general algebraic method.
Okay. And I don't know if somebody else wants to ask a question, but I also had one for number 4.
number 4 was a mean one.
4 was the mean one, right? Tell me 4 again. Remind me who 4 was.
I don't remember that one as well, but I think it's the square root of e to the x plus 1.
Okay, and it was an arc length or a surface area?
Yeah, I think it was surface
Surface
area.
area.
Right,
Surface
so-
area around the x-axis.
Okay, so we've got this guy to the half power. So its derivative is going to be 1/2 e to the x plus 1 to negative half power times e to the x because it's a general.
Yeah.
If you take it, square it and add 1, you get 1 plus this lot squared, which is 1/4 e to the 2x, e to the x plus 1 to the power of -1. That's squared, this squared. Now I'm going to rewrite this. Like that.
Wait, how did you get to the -1 power there?
I have -1/2, and when you square it, you double the power. So -1/2 doubled becomes -1.
Oh, okay. Yeah.
Now what I'm going to do is I'm going to combine these two together. So you end up with this guy instead of 1. And leave this guy alone. And distribute and rearrange the top line. You get this guy plus 4 lots of this guy plus 4 over this fella. And then I look at that top and I say, oh, you're a perfect square.
That's what it was hiding. I couldn't find the perfect square in this one.
Right.
How
That's
would
it.
you know if that's a perfect square or not?
There are 3 terms. Whenever I see 3 terms, I think perfect square.
So is there always going to be a perfect square if there's three
Well,
terms?
to be fair, it would have to be. Otherwise, the question would just disintegrate into a non-solvable solution, which was fine, because if it was, wouldn't you just use your calculator and it would say 84 decimal places and you wouldn't worry
Yeah.
about trying to make it look pretty. But
Okay.
since it's got 3 terms, it's a perfect square. So
So
when you
for these problems, it's just safe to assume that it's going to be a perfect square.
if there are 3 terms on the top, that's the
Okay.
proviso. Yes. Right, now if you stick that inside the square root, you get that guy and you get 2 of these guys. But remember the 2 pi f of x, which is this guy,
Yeah.
times essentially this guy. And it's almost like magic. Kill, 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 kill. And what you're left with is a pi. And a very simple integral.
Huh.
That's the kind of the magic of the algebra. How it can be your friend, right? It can get you out
Yeah.
of real messy trouble. Okay, I'm going to have to
Okay.
leave you guys, and I shall see you tomorrow.
Thank you.
Have a good one.
Thank
You too.
you.
Okay, bye-bye.